Hello students. So today we are going to start the most important part of the chapter simple harmonic motion, and that is what? That is how do we calculate the time period of a particle or a body which is performing an SHM. Okay, so let's see guys. So actually if I talk about, there are three methods in general are there which we use to find out the time period of a particular body. Okay, so the first important method that we have is force method. Force method. Okay, the second important method is, we can say, the torque method, and the last one that we are having is energy method. Energy method. Okay, this method is very helpful for those kind of particles which are performing linear SHM. Okay, so which are performing linear SHM, there we use this technique. Okay, and if you are dealing with the particle which are performing, or a body which is performing a what, angular SHM, then we go with this idea. Okay, so the when we see that there is a angular SHM is getting performed, then we use this torque method to calculate the time period. And the versatility of energy SHM is what, that it can be used for both the cases, like if the body or particle is doing linear SHM or angular SHM, it does not matter. Okay, it can handle both the cases very easily. Okay, because in this case you don't need to play with the vectors and all. The things are what, in the scalar only. Just we know that the energy is going to be what, conserved during the whole SHM motion. So using that idea only, we can find out the time period. How do we get all those things, we are going to see in the maybe the next lecture. Okay, first like maybe today's lecture I'm just going to focus on the force method. We will see some examples on that, then one more lecture on the torque method, and then one more lecture on the energy method. So like this way we are going to follow. So today I'm going to talk about what is the force method. Okay, so let me write down specifically force method. Okay, so there are certain steps that we have to follow. Okay, if you just follow step by step those steps that I'm going to mention here, then we can very easily find out what the time period of that particular particle or the body performing the SHM. Okay, so guys, let's see the step 1. Okay, step 1. So what is the step 1? Define the origin. Okay, define the origin. Define the origin. In general, in general, in general, in general, we will take the mean position, mean position as our origin. Okay guys, so this is the thing that you have to keep in mind. The first thing that we have to define as what, origin. So in general guys, wherever the body is in equilibrium, that position we will define as a what, origin. Okay, then step 2. Step 2, displace the body, displace the body from its equilibrium position, equilibrium position slightly, and calculate the net net restoring torque, restoring restoring force, restoring force acting on it, acting on it towards the mean position, towards the mean position. So guys, we have to do what? We have to just we have to displace the body along the path where we can have that restoring force. Okay, you will get that idea automatically, and then we will see that what is the restoring force we are getting in that direction, which is trying to bring the body towards what? The mean position. Okay, so that is the second thing. And then step 3, what is step 3 guys? Compare it, 1 minute guys. Step 3 I can write like this: uh, use Newton's second law and calculate the acceleration of the body using above net force calculated in step 2, calculated in step 2, and compare it with equation minus omega square x minus x naught. Okay, minus omega square x minus x naught, and find the omega, find the omega, and so the time period, and so the time period. So these are the guys what? 3 simple steps that we have to follow to find out what? To find out the time period of a particle performing an SHM. Okay, so let's start with some simple examples, and then we will complicate and we will take some more good examples to understand how do we use it. Okay, but remember guys, one remark I am giving you here, remark. Okay, the remark is that whenever you are dealing with spring block system, spring plus block system, okay, and motion is happening, motion is happening under gravity, under gravity, it is suggested, it is suggested suggested to use mean position, mean position at the position of the particle when spring is, when spring is at its natural length, at its natural length. This is guys what that I advise. Okay, because see, uh, when even if you want to take the mean position as a equilibrium position, then also you can do the problem. But what I feel that when we take the natural length and then we consider the position of the particle as the origin, the equation becomes very easy. We don't need to do the some kind of a complicated math. Okay, not complicated, but somewhere the equation becomes bit fuzzy. Okay, that I feel. So that's why I avoid in these cases to deal the problem considering the equilibrium position as a what? As origin. Okay, I take usually, and I ask my students also, when you see this kind of situation, you always go with the what? Natural length of the spring, and take the position of the particle as a what? Your mean position. Okay, and then sorry, your origin, and then start doing the calculation. You will see that what I am talking about guys. Okay, I'll take some examples and you will get the clarity. So let's take guys some examples and let's try to understand what I am discussing here. Okay, so let's say problem 1, problem 1. So here, as if you see, the question is like this, that suppose if we have a spring like this, and this is a block, and this is M, and spring constant is given what, K, and let's say right now the spring is at what, at its natural length. So we know that, guys, this position is only the what, your equilibrium position. This position only is what, your equilibrium position. So we can call this as a what, origin. Okay, spring block system is there, but the motion is happening in a what, in a horizontal plane. There is no motion under gravity. Okay, so we can take the what, the mean position is what, here only, and even the spring is also at what, natural length, so we don't need to worry about. So guys, the mean position I have taken here at when the spring is at what, its natural length. Okay, now guys, the second step, the step 2 is displace the body slightly from its mean position with some amount. Okay, so let's displace the body from the mean position here. Okay, so guys, we have displaced it. Now what will happen, the spring will get elongated. Okay, the spring will get elongated, so there is a force we are going to experience in the horizontal direction towards the mean position, and this force will be what, kx, and the direction will be what, guys, in towards mean position. So we can write this force is equal to what, minus kx. Why minus kx? Because x, if we are taking as a positive, then kx is going to be what, negative. So this every time we have to do, so always keep this thing in mind. Okay, this is kind of a ritual that we have to perform every time. Okay, so if x we have displaced in the right side, the force is going to come in the what, left side, minus kx. Okay, so guys, now what we have to do, we have to write the Newton's second law. So Newton's second law equation says that what, F is equal to minus kx. F is equal to what, it is equal to mass into acceleration, that is equal to what, minus kx. So A is equal to what, minus k by m, 1 minute guys, k by m into x. And now we can compare this with this relationship. So guys, because mean position we have taken as what, 0 only, so x naught is going to come what, 0. So what we can say, we can say A is equal to what, minus k by m, x is equal to minus omega square x. So from here, if we compare these uh, two, what we can say, we can say omega is equal to what, under root of k by m. So the time period t is equal to what, 2 pi under root m by k. So you can see it's a very simple problem, but I have just told you that how do we solve these kind of a problems. Okay, now let's take 1 2 more easy problems. Okay, so that more clarity will come, and then maybe I'll take few good problems also. So guys, let's see, suppose we have this problem, problem number 2. Here the question says like this, that there is a two springs. Okay, there are two springs which are connected with a block M, and it has been said that there is a, like, they are connected in such a way that there is no change in the shape and size of the body is going to take place, means there is no bending is going to take place in this body. So when we are uh, displacing this, okay, the equal displacement will happen in both of them. Okay, the equal displacement will happen in both of them. So guys, if you see in this case, what we can say, we can say that, let's say if this is k1 and this is k2, and if I displace this by x, okay, if I displace this by x, what is going to happen, guys, this will elongate and this will also elongate, and this will experience how much force, k1x, and this will experience how much force, guys, k2x. So the net force that the body is going to apply on the body is going to be what, guys, k1x and k2x. So F resultant will be what, minus k1 plus k2 into x. Okay, so guys, A we can say directly, that is what, k1 plus k2 divided by m into x. So omega is equal to what, guys, it is equal to under root of k1 plus k2 by m, and the time period is what, 2 pi 2 pi under root of m upon k1 plus k2. Is the same problem also we can do with the idea of what, the combination of spring. We know that these two springs are what, connected in parallel, so the equivalent spring constant will be how much, guys? K1 plus K2. So you can replace these two springs with a what, a single spring, and that single spring will have how much spring constant, K1 plus K2, and using that idea also we can solve this problem. So both the methods are fine, just I wanted to like elaborate this thing in a bit detail, so that's why I went like this way. Okay, one more problem I'll take for you. Let's say this problem, problem number 3. Okay, problem number 3. You want, if you want, you can try by yourself also. Okay, let's see, guys. So this problem here, what I'm having one block, and I'm having two springs like this way. Okay, I'm having two springs like this way. This is k1 and this is k2, and right now the both the springs are what, at its natural length. Now if I want to find out the time period of this block, if it is performing an SHM, what would be the time period? This is the question. So guys, this is also an easy question. If you see, actually here, if I displace this particle x from here, let's say at this position, what is going to happen? This is going to be elongated and this is going to be compressed. So what is going to happen, guys? This one will try to pull the body by what force? We know that. What is the force, guys? It is going to be k1 into x, and this spring, it is going to push the body, it is going to push the body because it is compressed, and this is also going to apply how much force, guys? K2x. Okay, so if you see, both the forces are, if you see these, both the forces are what, in the same direction. Okay, both the forces are what, in the same direction towards the mean position. So it means we can say that F is equal to what, again minus k1 plus k2 into x. So the time period is equal to what, 2 pi under root of m by k1 plus k2. So it is sort of appearing like that they are like what, behaving like that these two springs are what, connected in parallel. They are actually not connected in parallel, but their behavior is very similar to like what, that they are connected in parallel. So whenever you see this kind of a situation, you can think like that what, you can assume them like they are connected in a parallel, and you can solve the problem, but actually they are not. Okay, but just behavior wise, mathematically, the mathematical expression for both of them is quite same. Okay, so guys, you can see these are a very easy questions that like by which you can see that how we have to use these steps and how do we have to solve the problems. Now let me take a few some good problems. Okay, so let's take one good problem, guys, and let's try to understand this question, and if you want you can try also. So problem number 4, problem number 4, problem number 4. So guys, I'm having this kind of a setup that there is a spring like this and it is connected to a pulley axle. Okay, and there is a block which is going, like the string is going over the pulley, like this is the setup. Okay, and spring constant is given how much, k. Now guys, the question is, if I displace this body from here, let's say by x, then of course it is going to perform this kind of a SHM. Okay, so what would be the time period of this? Okay, so if you want you can attempt this problem. Important thing is, guys, what, in these kind of a problems we have to take care of two things. One is the constraint relation, and the second thing is what, of course, the force equations. How do we write the force equations? So you should know two things. Okay, how do we relate the constraint? Okay, and then solving the problem. Okay, so if you want you can try this question. I'm going to solve by my way. Okay, so guys, let's see. The first thing that I'm going to do here is, suppose assuming that, let's say, spring is at its what, at its natural length. Okay, at its what, natural length, because now we are dealing with the what, motion under gravity. So guys, I'll assume that the spring is at what, at its natural length, and at that very moment whatever the position of the block would be there, I will call this as a what, my origin. Okay, I will call this as a what, my origin. And now I will displace the block by x. Okay, I will displace the block by x, because who is going to perform the SHM? Block is going to perform the SHM. So I will displace the block by what, guys? X. Okay, so now if you see, when I'm going to displace the block by x, there is a some force that it is going to experience. Okay, so first let's see what would be the picture now. So if I displace the block, what is going to happen, guys? The body will come here. Let me make with the red color only. The body will come here, and this would be the position of the block. So there is a tension in the string is going to come, and this tension is going to what, it is going to try to pull the body towards the mean position. Okay, so that is going to be what, your restoring force. So we have to see that what is going to be the tension force. So if you see the pulley, guys, so pulley will have this side tension, this side tension, and this side some spring force is going to be, let's say this is going to be kx dash. So we can say that T is going to be nothing but what, kx dash by 2. So if we can get x dash, our job would be done. Okay, so if you see, guys, if we use the slack and tight method, okay, slack and tight method, we can find out that how much is the elongation is going to happen in the spring when I am going to displace the block by x. Okay, so if you see, guys, if I displace this pulley here, and this is going to come x, then there is a slack will come in the string this side x and this side x, so this will go 2x. It means if this is going to be x displaced, then the spring is going to experience how much elongation in this, x by 2. Okay, so this is a very simple thing that I am hoping you understand. I'll explain again, guys, just try to understand. If I'll try to make it, okay, separately here. So guys, if you see, when the when the pulley was here and this was the picture, okay, now if think about it, as the pulley will go here, as the pulley will go here, let's say x, so here there is a slack will come x and there is a slack will come x. So to tighten the string again, the block has to move what, 2x. It means if the block has moved by x, it means the spring has been moved what, by x by 2. I hope you're getting my point. Okay, so if you have understood this idea, we can say that T will be simply what, k into x by 2 divided by 2, because x dash will be how much, guys, x by 2, because we have displaced the block by what, x. Okay, so the T is going to be what, kx by 4. So now if I write the force equation on the block, guys, okay, if I write down the force equation on the block, so it will be what, T upward and mg downward. So the force equation will be how much, F is equal to, downward, guys, I am taking positive, and upward I am taking what, negative. Downward displacement, guys, okay, this downward displacement I am taking as what, positive, and this side, guys, going is what, negative. Okay, this is convention that we are using. So F is going to be how much, guys, it is going to be mg minus kx by 4. Okay, now if you see, F I can take minus k by 4 common. It's okay, I'm taking k by 4 common. So what will happen, x will be there, and this will become what, 4 mg by k. Now let me put acceleration. So acceleration will be how much, it will be minus k by 4m x minus 4 mg by k. So guys, if you compare this now with this x minus x naught, we can see that our mean position is going to be at what, 4 mg by k. That is the one thing that if you want to find out, that is going to be what, guys, somewhere here. Let's say this is your mean position, okay, which is how much, 4 mg by k. Okay, and after that time period, if we want to find out guys, we know the omega square. This is what, k by 4m. So omega is equal to how much guys? It is k by under root of k by 4m. So the time period is equal to what? 2 pi under root of what? 4m by k. So the time period is going to be what guys? Under root of 4m by k. Okay, I hope this is very much easy for you to understand. Okay, so let me take one more problem guys, and then maybe one more lecture I will take on the linear SHM to give you some more insight, some more ideas, and some more good problems on the linear SHM. Okay, so I'll take one more lecture and then we will talk about the angular SHM. Okay, so let me take one more problem for you right now, and then one more video on the what, linear SHM only. Okay, so problem number 5. Problem number 5. So guys, in this problem what I am having is, if you want again guys, you can try by yourself. Okay, so this is a spring. Spring is connected to a string, and this is k, and this is a pulley guys, and there is a block m. Okay, we have to find out the time period of the blocks SHM if it is displaced slightly from its mean position. Okay, so that is the question for you. So let's see guys, if you want you can try by yourself. I'm going to discuss this question. So guys, let's see. So the first thing that I have told you, that take the spring at its what, at its natural length, and consider the position of the block at that moment as what, your origin. Downward we are taking as what guys, positive, and upward movement we are taking as what, negative, as a sign convention. Now what we will do, we will displace the block by a small displacement downward, let's say, because we are taking x as a what, positive. So let's say we have displaced the block by x downward. Okay, now guys, here it is going to experience some sort of tension in the upward direction and mg in the downward direction. We have to find out the tension, then only we can find out the what, restoring force. So guys, to find out the tension we have to understand what is the elongation is going to happen in the spring. Okay, so if you see guys, I'll again show you the constraint relation between the pulley and the block. Okay, and through that we can find out this. So guys, if you see, suppose this is your pulley right now, and this is your block. So guys, if I displace the pulley by x, so there is a x slack is going to come here and x slack is going to come here. It means to tight the pulley, okay, sorry, to tight the this spring plus string combination, what we have to do, we have to compress the spring by 2x. Okay, we have to compress the spring by 2x, or if we elongate, sorry, if we pull the block by x, if we pull the block by x, what we are seeing is, we are seeing that if we pull the block by x, we are going to see the elongation of 2x in the spring. Okay, so both the ways you can understand. If I take the pulley up, okay, so if I want to tight this combination guys, okay, if I want to make this combination tight, what I have to do, I have to compress this spring, because string can't be change its length. Okay, but this can be compressed, and then only what, this length will become equal to what, this. Okay, because this end is fixed. Okay, so what you have to do, you have to only one place, that you have to compress it. Okay, so when you compress it, then only the string plus pulley system will be what, tight. And we know that during the whole motion the pulley and string will be always what, on each other. There is no slack, nothing is going to happen. So in the similar way, if I can say, if I use the reverse idea of this, if I elongate, sorry, if I pull the block by x, I am going to experience that there is a elongation of 2x is going to happen in the spring. Okay, so with this constant relation we can say that because I have displaced the block by x, I am going to experience a 2x elongation in the spring. Okay, so there is a 2x elongation is going to happen in the spring. Now if I make the FPD of pulley, so guys, there is a force is going to happen like 2kx in the spring is going to come. So this whole system is going to experience this side 2kx force, and this side is also what, 2kx, because throughout the body, throughout the spring plus string, the force is going to be what, same, because it is a light spring plus string combination. Okay, so this is 2kx, this is 2kx, so this force is going to be what, it is going to be 4kx. Okay, this is going to be what, 4kx. So the tension that we are going to see here is what, 4kx. So now guys, if I write down the force equation, it will be what, it will be simply mg minus 4kx. Okay, so if I take minus 4k common, I'll get x minus mg by 4k. Okay, and acceleration is equal to what, minus 4k by m x minus mg by 4k. So x naught is going to be what, mg by 4k, that is the mean position of the body, and omega is equal to what guys, under root of 4k by m, and so the time period is equal to what, 2 pi under root of m by 4k. Okay, under root m by 4k. So you can see guys, these are some good problems and the techniques that we have to keep in mind to solve these kind of a problems. Okay, now in the next lecture guys, I am planning to cover few things. Okay, so there are some points that I am just mentioning here that we are going to cover. One thing is that we have to talk about spring plus sleeve system. Okay, and understand the equivalent spring constant method. Okay, this one thing that we have to discuss guys, this is very important because in a lot of problems this idea is needed. So this we have to see. Okay, this idea we have to see. And second thing is uh, rubber band plus block system analysis. Okay, this is also one of very important idea that these kind of problems might come, and we should know that how should we handle these kind of a cases. Rubber is a special kind of a elastic body. Okay, so we have to understand that idea properly. So these two things guys we have to understand first. So in the next lecture I am going to discuss these two things in very detail, and then maybe we can move towards what, the torque method. Okay, so that's it guys for today. I'll see you in the next lecture.